Jnanam Paramam Dhyayam. Knowledge is supreme.
So, we will continue our study with Hilbert-Samuel polynomials and its connection with the dimension. So, let us recall what we did in the last two lectures. So, we had a graded ring R M and a graded module over R So, when you do it for the ring, you have a positive non-negative grading, n grading, and for a module it is z grading, and we are assuming that M is finitely generated, M is finite R module. Which is equivalent to saying that it can have only finitely many negative components, and all modules, all homogeneous components are modules over R0. So, R0 modules MM are finitely generated. These are our assumptions. And also we assume that this R0 is Artinian ring. The simplest way to think is that is equivalent to saying R naught is Noetherian and every prime ideal is maximal. This simply means the dimension of R naught, cool dimension of R naught is 0. So, in this situation we have considered this function. So, that is the function from z or n to n, namely any m goes to length of mm as a R naught module. This length is finite because we are assuming MMs are Artinian R naught modules, and to this we have associated a series which we call it Poincare series. That is P, it depends on M, and I want to also write that variable Z. So, this is by definition, this sum is running over M, it is length of mm, this is the coefficient of Z power M. Remember that when I did in the one more earlier lecture that I had, instead of length I have used a dimension. That is because I was assuming that time this R naught is actually a field, and what we proved is this has a special form. If you assume R is, now assume R is standard graded R-naught algebra. This simply means R as a R-naught algebra generated by finitely many elements, and each element, all these xi's are homogeneous of component, homogeneous degree 1. So, that is R1. And in this case what we proved is this Poincare series of M is of the form, first let us write it for R. So, it is of the form some Laurent polynomial Qm divided by 1 minus z power n plus 1, where Qm is a Laurent polynomial. So, that is Q z power plus minus 1, and we are discussing about the degree. So, first let me now make it more clearer. So, when one says somebody is a function, so recall in general if you have a function, numerical function f from z to q, such a function is called a numerical function. We will say that this is a polynomial function, is called a polynomial function if there exists a polynomial gx over with rational coefficients such that f of n equal to g of n for large n. Large n means so this means there exists n naught with this equality holds for all n bigger equal to n naught. So, first note that such a polynomial g must be unique, because if there are two polynomials which satisfy the same equality, then those two polynomials agree on many rational numbers, infinitely many rational numbers, and therefore, they have to be equal. So, note that such a polynomial g with the rational coefficients is unique. So, therefore, in this case the coefficient, leading coefficient of g, I will keep calling this is to be the leading coefficient of the function f. So, this is leading coefficient of f. This is the definition of a leading coefficient of f. Similarly, the degree of g, this is degree of f. So, for a numerical function which are polynomial functions, we have defined this leading coefficient and the degree of the. Okay, and also we will use a convention here, degree of a zero polynomial, degree of zero polynomial to be equal to minus 1. This is a convention. A degree of a zero polynomial is not defined, but okay. Now, how do we decide some numerical function is a polynomial function or not? So, for that you define a new function. This is something like a derivative. So, the new for a numerical function f, define df. This is also new map from Z to Q, which is defined by any n goes to f of n minus f of minus n minus 1. So, this is a new function, and then now in simple lemma we will prove so f is a numerical function and r is a non-negative integer, then f is a polynomial function of degree less equal to r if and only if df is a polynomial function of degree 1 less. So, first we are proving this. This is pretty clear because see, look at df at n is by definition f of n minus f of n minus 1. So, if f is a polynomial function, the leading coefficient of this right hand side is the same and the degree is same. So, we will get the leading coefficient will get cancelled. So, for large n, this is the difference of two polynomials of the same degree and same leading coefficient. So, it is clear that df is polynomial function of degree less equal to r minus 1, because we are assuming f is of polynomial function of degree r less equal to r. Okay. So, conversely, this way we are proving the assertion by induction on r. So, we have now given that df is a polynomial function of degree r minus 1 and we want to prove f is a polynomial function of degree less equal to r. Okay. So, if r is 0, r 0 means this df is a polynomial function of degree less equal to minus 1. So, that only means that df is a 0 polynomial. That means df, so this means df evaluated at n is 0 for large n. So, this means that f n minus f of n minus 1 is 0 for large n, but that means f n is actually constant. F n is constant for large n. That simply means that constant. So, f, therefore, f is a polynomial function, and because it is constant, degree is less equal to 1. So, that implies f is a polynomial less equal to 1. So, that proves the assertion for r equal to 0. Now, assume that we have assume r is bigger than 0 and df is a polynomial function for of degree less equal to r minus 1. So, df will agree to some polynomial g for large n, where g is a polynomial with rational coefficients a 0 x power r minus 1 plus a r minus 1, these are rational coefficients. degree of G is less equal to R minus 1. Okay, now just from here, what is f of n minus g of minus f of n minus 1 g of n, which is what I am going to do is just take a naught divided by r n power r minus n minus 1 power r. If I take this plus hn. So, whatever the remaining terms I club with hn, where hx is a polynomial is also in qx, and the degree of hx is smaller or equal to r minus 2, because I have taken the top degree terms here. Okay, because this n power, when you expand this term by binomial, n power r will get cancelled and there will be r here, and then that. So, therefore, hx is a polynomial of degree less equal to r minus 1. So, now you define f prime. This is a new function from z to q, defined by f prime at n equal to f n minus a 0 by r times n power r. So, this precisely tells us that d of f prime at n is that remaining residue, that is hn for large n. And because degree of h is smaller or equal to r minus 2, this d f prime is a polynomial function of degree smaller or equal to r minus 2. Therefore, by induction hypothesis, f prime is a polynomial function of degree less equal to r minus 1. And you shifting this term to the other side, you get then f is a polynomial function of degree less equal to r. So, that proves the lemma. So, recall that we have proved that if you take this Poincare series, it is a rational function of the special type, and the coefficients, then the coefficient. So, let us write it. So, let me write it as a corollary. Is Pm Pr, let us Prz, this is like definition was, this is Fn t power n, not t, z power n m, and Fm was the length of as a R naught module Rm. So, this Fm, then Fm is a polynomial function of degree less equal to n minus 1, and remember this n was what? This n was the number of the number of R0 algebra generators of R. That is n minus 1. So, proof: just note that the formula, if you have R positive, then that, remember this we have written in the form Q by 1 minus Z power R. I forgot something. I forgot that when we have a rational function like that, if a numerator also has at 1 equal to Q at 1 is 0, then we cancel the numerator, this 1 minus Z part there and below also. So, we have this, now below is R and this R has to be less equal to n minus 1, n R has to be less equal to n. So, note that this is equal to summation d this f at n, this one Z power m. So, therefore, by induction, the assertion follows by induction by using the earlier observation. So, use induction with earlier lemma. So, just let me note formally what we have proved. We have proved the following theorem. So, R is a graded ring, n graded, and with R naught Artinian, and M is graded, finitely generated R module, and R is standard graded, means R is R naught and generated by few elements x1 to xn, where degree xi are 1. Then what we call it HM, this HM, think of this is a function from Z to Q, any M going to length of as a R naught module of MM. This is a polynomial function of degree less equal to n minus 1, where n is this number of R naught algebra generators of this. This polynomial, so there is a unique polynomial associated to this numerical function, and that polynomial is usually called Hilbert-Samuel polynomial of M. So, that is a polynomial associated to this polynomial function. And so these polynomial has a degree and leading coefficient. So these two invariants, the degree we are preparing to prove that the degree of this polynomial is actually the Krull dimension of the module, and when the module is R, then it is the Krull dimension of the ring. That is what we want to prove.